Okay, we're going to work problem 6.82 from the end of chapter questions. This problem is pretty important. I'm pretty confident you're going to see this in the homework, and I'm pretty confident you could see this type of thing on the exam. You know, in general, these problems that I work, I feel like they could show up on exams. Can't guarantee anything, of course, but it's certainly very common to see this type of problem on an exam. We're asked to use heat of formation, standard heat of formation data, to compute the delta H reaction, or the standard enthalpy of a reaction. The way these problems work is you're typically given a chemical equation. In some cases you have to balance it. In part A of 682, they're actually giving you a balanced equation. This stuff reacts to make this stuff, okay? It's balanced, you get the idea. How do we compute the standard enthalpy of reaction? This should be with a zero here to know the standard, okay? Well, we're going to use essentially the Hess's law approach, okay? Which basically says enthalpy is a state function. Doesn't matter how you get from point A to point B, as long as you get there through a particular route from particular reactants to particular products in particular phases or states, the enthalpy is a state function. The enthalpy change is conserved, okay? So as a result, we can use this summation law to compute the delta H zero reaction. Let's see how that works, okay? If we look at the law closely, it's telling us to add up or sum the product M, which is the stoichiometric coefficient of our products, here it's a 2 and a 2, times, multiplied times, the delta HF0 products, okay? So each of the individual compounds in our equation has a heat of formation, standard heat of formation that could be associated with it. And what we're to do is to find that standard heat of formation, usually from data tables, multiply it times the stoichiometric coefficient, add together the terms for the products, and subtract the analogous terms for the reactants. If we do that, we can come up with delta H0 reaction. So let's work our way through this to see how it would work. It's pretty straightforward, actually. It's simple once you get the hang of it. With me just describing it in words, it's probably pretty confusing at this point. But let's look at a sample problem to see how this works, okay? So what we got to do is add up a term for the products first, okay? And then we're going to subtract term for the reactants from the balanced chemical equation. So what is the equation, or what does this tell us to do? All right, well, we're going to add things. We're going to add a term for every single product that we've got. Now here we've got 2 products. So we're going to have 2 terms that we need to add together. Okay, so I'll write some brackets, 1 for each term. We're going to have 1 term for SO2. And since the stoichiometric coefficient in the balanced chemical equation is 2, I'm going to multiply that 2 times the delta HF0 for SO2, or sulfur dioxide. Each compound has their own characteristic delta H0. The delta HF0 data in kilojoules per mole is listed over here on the left. Now this is not given in the problem. This is pretty standard. You either have to find these values within the chapter or more generally in Appendix B of your textbook. It's at near the very end. There's an Appendix B. It's got all these heats of formation data in it that you will need to work the problems in the book. Okay, that's where I got these from, the Appendix B. Now the value for SO2 is negative 296, so negative 296.8, and that's what I'm going to plug into this equation. But what I want to caution you of a couple things, okay, that you got to be real careful about when you're doing this. It's easy to make a mistake. You need to look for what phases, not only the compound identity, but also what phases are present in your balanced chemical equation. Here the SO2 is a gas, which is the sort of standard phase for SO2. But in some cases, different compounds will have different options. So for instance, water. If I look at Appendix B, I'm going to find a number for the gas phase water. I'll also find a number for the liquid phase water, okay? I need to use the right phase because the numbers are different. They're not the same. And if you use the wrong number for the incorrect phase, you'll get the wrong answer. Okay, so you got to pay attention if it's a gas, liquid, solid, so on and so forth. Okay, so for SO2, I use the right value for the gas phase. We're good to go. Okay, moving on. Again, what this tells me to do is to add up or sum the terms for all the products. I need to add in the term for water. The stoichiometric coefficient, which is the lowercase m, is also a 2 for water. It doesn't have to be, but in this case it is. And I'm going to multiply that by this negative 241. Negative 241.826. And that's also in kilojoules per mole. Here, all these units are kilojoules per mole. So now that I've completed this process of summing my terms for the products of the reaction, the stuff that's on the right, I'm going to finish the equation by summing a similar term for reactants. Okay? Now, what are my reactants here, and how many do I have? Well, it looks like I've got 2 different reactants. I need to add the contributions for both of them together. That's what the summation business tells me. It tells me, again, I need to take my stoichiometric coefficient and multiply it by the value for each one. Okay, so let's start with the H2S. Stoichiometric coefficient's a 2. It's H2S gas, and the value in kilojoules per mole is negative 20.2. That's associated with the H2S. Now, what about my other reactant? Okay, well, the stoichiometric coefficient's a 3 for oxygen, and now I'm going to multiply by oxygen's value, its standard enthalpy of formation. Well, lo and behold, if you go to the data table, you find that the value for oxygen gas, O2 gas, is 0 kilojoules per mole. This is because oxygen is diatomic in its native form as a gas. This is an element in its standard form. And by definition, the standard enthalpy of formation for elements in their standard forms is a big fat 0. Okay, now your data table in Appendix B is actually pretty kind to you because they list the value of 0 for the delta HF for these elements in their standard forms. Other data tables that you might find in different books or also on an exam might not be so kind. They might expect you to know that that's the case. So for any element in its standard form, standard enthalpy of formation of 0, okay? So that could trip you up, like on an exam, if we expect you to just know that, okay? We don't give you a value and you don't know it's supposed to be 0, you know, you're kind of stuck at that point, okay? But fortunately for this case, it's 0, and that's going to simplify the math some. Now, another thing to be real careful of, okay? Just because you have an element by itself and not combined, it doesn't mean that it's always a 0 standard enthalpy of formation. It's got to be the element in the standard state, like here's the gas. If this was a liquid or a solid, it would no longer be 0. If it was atomic oxygen, just O without the O2, it would no longer be 0. Some cases, elements that form solids, the atoms in the solids can arrange themselves in slightly different ways, which make them so-called allotropes of one another. An example that's like a carbon. Carbon can either be graphitic carbon, graphite like what's in your pencil, or it can be diamond, both if it's carbon, but the atoms are just arranged in a different way. Only one of them is going to be the standard state. In the case of carbon, it will be the graphite case, okay? So only one's going to be the standard state, and only one is going to have that 0 value. Other forms will have different non-zero values. But anyway, it's 0 for our oxygen here, and mathematically we can now proceed. So if I do that, over here on the right, I'm going to end up with a negative 40.4 kilojoule per mole. 0 just kind of goes away, and I just have to multiply the 2 times the negative 20.2, which yields a negative 40.4. Notice here that I'm also trying to be real intentional about keeping track of the negative and positive signs. Okay, that's another place that students can make mistakes. You really want to keep track of what's negative and what's positive. Don't lose track of those negative and positive signs, or you'll be in a little bit of trouble. This term on the left, if I multiply out and add everything up, ends up being negative 1077.252 kilojoule per mole for my products. Okay, so I have a negative 1077.252 minus a negative 40.4. Okay, so that, of course, kind of these negatives sort of undo each other. It becomes a positive over there on the right, and as a result, my expected enthalpy of reaction for this reaction is a negative 1036.852 kilojoules per mole. This is the enthalpy, the standard enthalpy of reaction for this reaction. Okay? So this is a powerful approach because I can write any reaction that I want here, and I can find my standard enthalpy that's associated with that reaction. All I need to do is look up these numbers in Appendix B in the back of the book. These are the heats of formation for each of the compounds that are involved, and follow this simple equation, relatively simple equation, and I can compute my enthalpy of reaction. All right, before we're done, let's try one more of these because this is, again, an important problem type. Okay, so I'm going to erase what I got here. This video will be a little bit longer than the other ones, but that's okay because we need to know how to do this. I'm also going to erase the reaction. This is going to be part B of 682. Now in part B, we are told that CH4 gas, which is methane, oftentimes you hear about methane, a major component of natural gas, that's CH4. It's going to combine with chlorine. And here I'm actually balancing the equation for us just to save time. I'm assuming that you're able to do that. I just balance the equation. It's not given to you balanced, okay? So that's actually one thing that you need to do on your own. Okay, but I went ahead and balanced just to save time. And then I already looked up the standard enthalpies of formation from the back of the book in Appendix B, as in boy. 74.87 kilojoules per mole for methane. CCl4, which is called carbon tetrachloride, in its liquid form, has a standard enthalpy of formation of negative 139 kilojoules per mole. And HCl gas, this is hydrogen chloride, not the acid, because it's not aqueous, it's a gas, which makes it hydrogen chloride gas, has a delta H formation value of 92.31 negative kilojoule per mole. Those are the numbers from the back of the book. Now, how do we go about solving this? Well, we use the same exact equation, just for a different reaction, okay? So knowing this equation, knowing how to use it is obviously really crucial here, okay? So what do? Well, the equation tells us to subtract one number from the other. So I'm going to set up my big square brackets, one for the products, one for the reactants, and then I just need to go fill in the blanks, okay? It's always products minus reactants. So I need to sum terms, one for each product. There's two products. The carbon tetrachloride has a prefix of 1 in the balance, or stoichiometric coefficient of 1 in the balanced chemical equation. So I'm going to multiply 1 times its standard formation enthalpy. And for CCl4, that was negative 139. Note that that's a liquid. The value that I'm giving you here is also for the liquid phase. So 1 times negative 139 is what we need to do there. We need to multiply 4 times the value for HCl, which is negative 92.31. Notice again, being very careful to keep the negative and positive signs. Now from the term for the products, I need to subtract similar term for the reactants, okay? How many reactants do I have? Looks like I have 2, right? This guy and this guy. So the methane has a prefix of 1, the chlorine has a prefix of 4. From the balanced chemical equation, I need to multiply 1 times methane's enthalpy of formation, which is negative 74.87. And then I need to multiply 4 times chlorine's value. Oh, no, wait. Where's the chlorine value, right? There's no value for chlorine. chlorine gas, that is Cl2 gas. Of course, I purposely did this. This is chlorine gas in its sort of native natural state, standard state. As a result, it gets a value of big fat 0 for its enthalpy of formation, just by definition. Okay? That, again, makes things a little bit simpler because that number just kind of goes away over there on the right. So what we have is 1 times the negative 74.87 here. I'm keeping that sign. I'm also keeping this negative sign. Okay, again, got to be really conscious and careful about keeping those signs. I've kind of been there and done that already myself, so I understand how easy it is to lose track of some of the signs. If you add this together, you get negative 508.24 kilojoules per mole. All these have units of kilojoules per mole because I've kind of been not paying too much attention to that. Again, the negative and the negative, so like this becomes a positive since we add it back in. And the net result is negative 433.37 kilojoule per mole. And that is my delta H zero reaction for that reaction. So my standard enthalpy of reaction for methane reacting with 4 Cl2 to make carbon tetrachloride and 4 copies of hydrogen chloride gas should be negative 433.37 kilojoules per mole. Again, we computed this from tabular data. That's in the back of our book. And the cool thing about this is we can write any reaction we want as long as we can balance it. We can predict what the standard enthalpy is for that particular chemical reaction just from all this tabular data. And that's really the beauty of this Hess's law business, and the fact that the enthalpy is a state function. It doesn't matter how we get from these reactants to these products, as long as we start with these guys in these forms and we end up with these guys in these forms, that is the enthalpy of the reaction.